It's my pleasure to present our next speaker. So Carey is from Intel. He was actually the hardware lead for Nervana, which was acquired by Intel, and he's now senior director at Intel. Carey?
Hey there. So I'm excited to go after Vincent's talk because I thought that was really good. So everybody's probably awake. I apologize to the follow-on speakers. I'm Carey. I was at Nervana very early. I was employee number 1. Led the hardware effort. So I've been working on deep learning architecture for a little while. Rather than just kind of go through a product roadmap, I thought I would focus on a particular area of interest with deep learning hardware, right? And that's memory bandwidth. And so whenever we talk to HPC folks, a lot of times they'll say that they want memory bandwidth more than they want flops, right? They say we're limited by memory bandwidth, not by flops. And then they get a faraway look in their eyes and say, man, I wish we were doing deep learning. That deep learning, you can throw flops at it until the cows come home, and you don't need, any memory bandwidth for it. So I figured we would talk about that. So in reality, you can throw flops at deep learning, at the bigger gems, at the bigger convolutions, right? But if, let's say, hypothetically, your runtime is 70%, one of these easy to parallelize operations, and 30% something else, batch norm, as Vincent mentioned, or ReLU. That means that your maximum speed up in the biggest die in the smallest node is still only 35%, because pretty much any hardware today is going to be able to max out memory bandwidth with an element-wise operation. So, what can we do about that, right? That's what this talk will be. Okay, so just some background, and I think this is probably clear to everybody, but gem and convolutions, as long as they're big enough, have almost infinite data reuse, and you can utilize all the flops you want, with a reasonable memory subsystem, right? But if you look at the gems, for instance, one of the dimensions is usually mini batch. So when you see a 4K by 4K matrix multiply benchmark, it's usually 4K by 4K by 4K, which is an incredible amount of data reuse. But in a real deep learning operation, it's going to be 4K by 128 by 4K, or 4K by 32 by 4K, right? Which is pretty easy to become memory bound on the highest end teraflop processors of today, right? So another one that is particularly bad and has been mentioned earlier is one-by-one convolutions. I think they were actually designed in order to deal with small memory sizes and small teraflops. But now that we have lots of memory on die, and we have lots of HBM memory on package and lots of flops, the one-by-ones are just forcing us to not get good utilization of the flops, right? And then, like I mentioned, any element-wise operation is by definition memory bound on any current hardware. So what's the next problem? The next problem is you can't fit this stuff in SRAM, right? Even a 4K gem might have weights of 32 megabytes, right? And so that right there is going to wipe out most of the memory on a current chip, if not more than all the memory on a current chip. And when I say memory, I mean SRAM, right? If you look at a couple of these layers are from one of the ResNets, and you've got hundreds of megabytes of data in terms of the IFM, OFM. So if you really want to get the maximum data reuse, you're bringing data in and out of the memory all the time. You can't get the maximum reuse because your die can't store all the memory, right? So kind of a simple graph, and I know that nobody can read it, so I'll explain it. The three sets of bars are 3 different HBM speeds, right? And we're assuming 80% utilization in this. And so the one on the far left is 1600, which is kind of the current state of the art. The middle one is 2400, which will be out, potentially be out next year. And the one on the right is something that won't be around for a while, if at all, and it's 4,000, right? And so each bar is a layer, right? So the first 2 bars are gems. And the basics are the difference between the light color and the dark color bars is the mini batch. So I drew the red line at 100 because 100 is possible in this generation, right? But in the next process technologies in 7 or 5, the memory interface is not going to get that much bigger. You're going to get twice as many flops, right? And you're going to just end up idling half of your flops, right? So another interesting one, those 2 tiny bars are n equals 1 convolutions. And then the bars on the right-hand side, the difference is, I think, 3 by 3 versus 5 by 5, right? So you can see what happens with, if you use a slightly bigger filter, you can utilize a lot more flops. And so this becomes a discussion, kind of as Vincent mentioned, between the hardware architecture team and the data science team, right? This is what the hardware can do. You can potentially get more speed up if you use maybe a bigger filter. And we now have enough teraflops and enough memory to do that. So, feel free to keep using the 1x1s, but you're not going to get full utilization on your hardware, and you're going to train the same speed maybe as a 3x3, right? And so maybe that 3x3 would have been better. Okay, now this is the ideal case. This is the case where we bring everything into the chip one time and run it all in one shot, which is impossible, as we talked about, because of the data sizes. So I just added one extra read-write of all the data, and of course all the numbers went into half, right? And you can see even with next year's state-of-the-art HBMs, that last bar is barely over 100 teraflops, right? Now this is a little disingenuous. I don't want to make people not go build hardware for this, because these are very small convolutions. In a larger size convolution, I had to take them off the table because they blew the scale of the table way out, right? And you couldn't see any of these bars because they were way down at the bottom. So, don't be worried about building hardware for this, but like I said, it has to become a discussion with the architecture team and the data science team. Hey, maybe you can get better performance by changing your network a little bit to utilize more flops in the same training time. So to summarize, the intermediate state, blows out the SRAM that can be reasonably fit on a die. And there are a number of limitations which will make certain layers of a network memory bound, right? 1x1, batch norm, right? ReLU, etc. So from an architecture point of view, what can we do? So this is the only die in which I really talk about stuff that Intel Nervana is doing on its product line. The first thing is, starting on the left, the data size and the data format is very predictable. We know exactly what's going to happen, and we've designed the chip for deep learning. So we were able to choose a memory chunk size of 2K bytes and fit that into our memory controller so that we always hit within pages, right? And so in the ideal case, or a decent portion of the time, we don't have any bank conflicts or any bank group conflicts in HBMs, so that we get more basic utilization out of the memory bandwidth that's available than perhaps a more random memory controller would be, a more general purpose memory controller, right? Another thing we do is we have large SRAMs inside each processing element as opposed to a cache hierarchy. And again, this is because we're designing for the deep learning specifically. And so we know ahead of time where everything needs to go, what it all looks like, and and we're writing kernels to make best use of the chip. And so there's really no reason to have a cache. This way we have kind of direct control in the kernel of what data is where it's going next, and how to move it between PEs or even between chips, right? And that last bit is important because we also have an internal data network which moves the data between the processing elements or even between chips without touching the HBM memory subsystem, right? And so what that does is it makes the sea of processing elements look kind of like one big processing element, right? And if you're doing a gem, you effectively get kind of n cubed compute based on n squared data. And so the bigger your chunk of compute is, the more benefit you get from having that large chunk of compute, right? And of course, in this case, we're not going to the HBM unnecessarily, so we get more bandwidth to try to be memory bound less often. Okay, so, boy, I'm going really fast. I tell you what, we're going to be done with this quick, and then we can move on. Everyone will go home early. Okay, so what are the things that we can do in the hardware in order to mitigate this problem? Obviously, the first thing is don't believe what you've heard. You need a good memory subsystem. You can't do it with DDR, so use HBM or HMC, right? The only time you could do it with DDR is if you can pull in all of the weights for whatever your network is, and then maybe for inference you could stream the data through the chip, and your weights are already on the die, and that'll be kind of your best case, right? The second one is maximize your SRAM size, and another reason for that is because you're going to have to double buffer. We already talked about the fact that everything doesn't fit on the die at any point in time, so you need enough local SRAM in each PE so that you can load one chunk of data, be working on one chunk of data, and load the next chunk of data. And in fact, if you're using that on-die network, you're going to have another set of double buffering. So you're moving data from PE to PE, from the HBM to the PEs, even to the SerDes. And so that's why we have such a lot of SRAM in each PE, right? And then of course we talked about page chunks and bank conflicts, right? And actually, now that I think about it, I should have mentioned on the previous slide, let's see if I can go back. Somebody might say, hey, what about all those high-speed SerDes, right? So we have a bunch of high-speed SerDes. Obviously, the TPU2 has a lot of high-speed SerDes. The new NVIDIA processors have a lot of high-speed SerDes, right? And so you might say to yourself, hey, maybe those high-speed SerDes are going to help us with this memory bandwidth problem, right? But typically, it scales linearly with the high-speed SerDes. So effectively, adding 2 chips, that means that you're cutting your training time in half. And it scales linearly for a pretty decent number of chips. And so if you're cutting your training time in half, and then each chip is reading half of the memory, effectively your memory read per time is the same, right? And so having the SerDes doesn't really help the memory bandwidth problem. Now, on the other hand, if each chip is working on a smaller chunk of the problem, you might be able to fit more of it into your local memory, your local SRAMs, and in which case it would help. So it's kind of a mixed bag in terms of the SerDes and the memory bandwidth. Okay, so moving on to the next slide. So we talked about this. It's important to avoid disturbing the HBM memory system or whatever your memory system of choice is. So there should be, in the ideal architecture at least, there should be some way to move data between processing elements without messing with the cache hierarchy. That also saves power, right? If all the memory is local to the multipliers, or as local as it can be, the power of moving the data between the memory, the local memory, and the processing elements is minimized, right? Similarly, if you've got multiple processing engines and you're passing data between them, as long as you're passing on the local network and you're passing to a neighbor, that minimizes the power used to move data around the chip as well, right? And of course, every time, all these things you're doing are mainly to minimize your memory, your external memory bandwidth, which is the biggest power hog of all, right? So another thing you can do is, kind of reduce the element-wise operations. Either get rid of them, right, or do them do them on the way out, right? So whenever you achieve a final product in your element-wise, or I'm sorry, in your matrix multiplier, your convolutions, apply whatever the next element-wise thing is to it, right? apply the activation, you certainly don't want to go back out to memory and then back into memory, or I'm sorry, then back into the processing elements to do an activation or a random sampling or something, right? That's a huge waste of time, right? The only time you really need to do that is something like batch norm, where if you do the full thing, you have to go through all of the elements in the memory one at a time, and then do it multiple times in a row. And even then, you should be able to do the first step on the way into the memory and cut it down to a couple steps, right? And then a couple things folks have talked about today, compression and or pruning, right, helps with memory bandwidth, obviously. If your network is filled with zeros, especially after training, right, there's really no reason to store tens or hundreds of zeros in between pieces of data in the memory, right? That's silly. So you might as well compress on the way in and out of the memory, right? Pruning helps with that because it adds more zeros into the network. Now, what about sparsity, right? What if we have sparse hardware? Well, sparse hardware goes the other way. Sparse hardware is getting rid of multiplies and increasing the load on the memory subsystem. So you can't kind of have your cake and eat it too. The combination of compression and sparsity effectively makes it kind of a wash if you support both. So the next one is something that a couple of the presenters have talked about, right? Basically, once you have a hardware substrate that is optimized for deep learning, whatever that substrate is, whether it's the new GPU with the tensor instruction or the TPU2 or our chip, you should, the data science team, should at least take a look at what the hardware does well and what it doesn't do very well, right? And anything they can do to, in this case, I'm looking only at memory bandwidth, to minimize memory bandwidth or increase data reuse and data parallelism is something that should be considered, right? And so obviously larger mini batches are always better, larger convolutions are always better, actually bigger filter sizes are typically better, right? Minimize element-wise operations. If somebody could think of a way to do batch norm in one pass, like that'd be great, right? And then something that was mentioned way earlier in the day, multiple times, is smaller bit widths, right? If you're storing 4 bits or 2 bits or 1 bit instead of 16 bits, which is our native thing, you're effectively multiplying your memory bandwidth, right? In fact, 3 years ago when we started this program, we went to 16 bits. That was doubling the performance compared to 32 bits of the memory subsystem, right? Now 16 bits is pretty much the norm through a variety of work, some of which was at Nervana. And so now we have to look at, well, what if we go to 8 bits or 4 bits or 2 bits at the very minimum for the storage, right? Okay, so to summarize, adding flops is easy, right? Every time you go down a process node, you can have effectively double the flops in similar power, right? Simplifying here. But feeding those flops is not always as easy, right? And so I look at it as a way for both the architects and the data scientists to work together to determine what's important in the next generation of processors, and then work together to bring the whole state of the industry up a notch, right? And then the obligatory AI products group slide, we have this is a brand new business unit at Intel. It shows that Intel is committed to AI. It's a top level business group in parallel to all the other big business groups. The Nervana chip family will be the first chip product, but we have Neon and Graph, right? And we're supporting cloud APIs. We have a new lab doing AI research, right? And so it's an exciting time at Intel. I'll pick up resumes at the door. Okay, and so that's pretty much it, actually.
Questions? All right, so I have a first question. So can you tell us a little bit about the programming stack that you're imagining for this? Is this something that you want programmers to write down the memory, is the data in and out schedule by hand, or
Yeah,
live?
so for Intel, we have the ngraph and we call it Argonne stack, right? And so similar to other processors, we'll supply kernels to do all of the layers, and we'll automatically distribute across as many processors as you have in the system, right? So the low-level kernels will take care of distributing using the SerDes between multiple chips or between multiple chassis, and the top-level API is we can connect to MXNet or TensorFlow.
But are you going to expose a low-level ISA here, or is it going to be like the GPU companies that never expose that?
Yeah, so we are not necessarily going to expose the assembly language. We will potentially expose our Argonne layer, but that's still over on top of the distribution layer. So the Argonne API is a little bit of a high-level API. It looks, kind of like a cafe kind of thing. And that's below that is the scheduling across multiple GPUs.
Questions? Yeah, Vincent.
So I'm sitting here and I'm hearing both Intel and NVIDIA telling me that the memory bandwidth limit is something that is kind of a fixed thing. Who do we talk to get more memory bandwidth? Or the buck stops with you guys?
There's things to do in the upcoming generations to get more memory bandwidth. The interposers are getting bigger, HBMs are getting better, but there is, to some extent, in the end, there's going to be a certain number of teraflops that can be applied to a certain number of HBMs of whatever genre. So now fortunately, that number of teraflops and that number of HBMs right now is roughly parallel in terms of the power you're using for the teraflops and the HBMs that are available. In the future, 7 or 5, we'll have to, like I said, figure out a way to get more HBMs attached to the die.
There's things better than HBM coming.
Yeah.
Nothing increase the speed of light, right?
Of course, yeah, that's the next thing on my
Not a
list.
latency problem, it's a bandwidth problem.
Yeah, latency doesn't matter. It's all about bandwidth here.
It will help too.
Are you worried about any programmability effort to this, being too hard to program this?
Well, so our chip, we've kind of built it for this purpose. The instruction set is basically a deep learning instruction set. So it's a linear algebra convolutional instruction set. And in fact, the only reason we don't break out the ISA is because of the parallelization across clusters or processing elements and across die. Like, we figure that 1 or 2 people working hard on parallelizing a convolution is going to be better than having the whole industry try to do the same thing.
But having local memories, you need to orchestrate the movement of data. Right?
Yeah, I mean, so we in our design, everything is a tensor, and so there's so we actually treat it's as if you're moving registers, and so it's like if you want to move a chunk of data from the host to the chip, and then from the chip to a processing element, it's the same kind of instruction set as moving a register, right? So you just do like effectively a move, and it's moving a 2 or 3 dimensional chunk of data into the processing element. So that's how we thought about it and tried to make it easier to program, right? And we take care of like dependency checking and stuff across the larger tensor, in the HBMs as well, just kind of inherent in the instruction set.
Do we have another question? I actually have one. I don't know if you will be able to answer it, but just in case. So do you plan to actually keep the Nervana product line separate from the Intel CPU product line, or are there any plans to actually, mix and match the two somehow?
Yeah, I can't really talk about that.
Thank you. Let's thank the speaker.